ETABS offers two powerful techniques for the application of accidental torsion when performing a response spectrum analysis. ETABS can include accidental torsion by either applying a static torsional moment to response spectrum results or by adjusting the location of the center of mass and running multiple response spectrum analyses. Codes typically require that response spectrum analyses include accidental torsion in addition to any inherent torsion present in the model. Inherent torsion is caused by the offset between the center of mass and the center of stiffness in a building, while accidental torsion is used to account for uncertainties regarding mass and stiffness, including the variability of live loads, as well as to account for the torsional component in a ground motion. The eccentricity required by most codes for accidental torsion is typically in the range of 5% to 10% of the building dimension perpendicular to the direction of the applied load. That is, if we are applying a response spectrum in the x direction, the eccentricity would be a percentage of the building dimension in the y direction. Many codes are similar in their approach to implementing accidental torsion. For this example, we will use the ASCE 7-10 code, and to simplify the input, we will apply a response spectrum in only the x direction. In order that the program can properly determine the dimensions of the building, diaphragms must be defined. We do this by going to the define diaphragms command. Our diaphragm may be either semi-rigid or rigid. Both will work for this accidental torsion study. We will select the rigid option for this example. We select the floors and assign the same diaphragm D1 to each level. Now we will illustrate the first technique where the accidental torsion is applied as a static torsional moment. First, we will review our response spectrum function. We have previously defined an ASCE spectrum. Next, we will check our mass source. We have a single mass source defined at this time. We will switch the mass source to use the load patterns. Dead plus a quarter of the live load. Now we will define our response spectrum load case. We will call our load case seismic. Select a type of response spectrum. And the mass source will be the one we just reviewed. We will apply our ASCE spectrum in the U1 or X direction. Remember that in this example we are going to apply a spectrum in the X direction only. The modal load case will be the default modal case, and we will use the CQC combination method. Note that we are leaving the diaphragm eccentricity set to 0 for the moment. We will come back to this option shortly. We are now ready to run the analysis. If we display the deformed shape in the plan view for our response spectrum analysis, note that the y displacement at the corner is virtually 0. This is because we have a symmetric structure and there is essentially no inherent torsion. Now we will show how we can easily add accidental torsion to this load case. Returning to the seismic case, the key to adding accidental torsion is the diaphragm eccentricity option. Clicking the Modify Show button, we will set the eccentricity to 0.05 for all diaphragms. The eccentricities may be overwritten on a floor-by-floor basis if so desired. Setting this value to 5% will apply a static torsional moment at each floor equal to 5% of the diaphragm dimension times the lateral story force. In our case, for the X direction spectra, this will result in an eccentricity of 5% times the Y dimension. Had a spectrum in the Y direction also been applied simultaneously, as might often be the case, an EX times FY would also be calculated, and the larger of the two torsional moments would be applied. In this case, the static torsional moment is applied at the center of the mass because we are using a rigid diaphragm. However, had we been using a semi-rigid diaphragm, the static torsions would have been applied at each node based on the story force at each node. Speaking of story forces, the story force is calculated by the program looking at the forces just above the floor and the forces just below the floor, and taking the difference to be the story force. The analysis is now ready to be rerun with the diaphragm eccentricity option set to 5%. Now, when we check the displacement at the corner, there is a small but still significant displacement in the Y direction due to the accidental torsion. However, this technique does not account for the amplification of accidental torsion that some codes require for torsional irregularity. The ASCE code, for instance, requires that the user look at the ratio of the maximum displacement over the average displacement, and if the ratio is greater than 1.2, the user must amplify the accidental torsion. However, this may take a significant amount of effort, as the displacement should be tallied at the modal level, and thus this may not be a trivial process. However, the ASCE code allows the torsional irregularity check to be omitted if accidental torsion effects are included in the dynamic model, which we will now show how to do in ETABS. This is the second technique discussed at the beginning of the tutorial, where the accidental torsion is addressed by adjusting the center of mass and running multiple response spectrum analyses. As stated a moment ago, the ASCE code allows the user to skip the cumbersome process of determining torsional irregularity if this technique is utilized. To include the accidental torsion effects in the dynamic analysis model, we need to offset the mass from its actual or calculated position. That is, move it by a distance equal to our code specified eccentricity in both the plus and minus directions. Since we are applying the spectra in only the x direction, we will be adding 2 additional response spectrum analyses. However, in general, you would typically be adding a total of 4 response spectrum analyses, 2 in each direction. We start by returning to the mass source command. We select the original mass definition and add a copy, which we will name mass plus y. We will use the same load patterns for the mass, but this time we will select the Adjust Diaphragm Lateral Mass to Move Mass Centroid by option. We will set the x direction to 0 and the y direction to a positive 0.05. This will move the mass in the positive y direction 5% of the y building dimension. We will add another copy, and this one we will name mass minus y. Again, we will adjust the diaphragm lateral mass, and this time we will set the ratio to minus 0.05 to move the mass in the negative y direction 5%. Remember that we are not applying any spectra in the y direction, so we do not need to define masses that move in the x direction. We have now moved the mass up and down to either side of the calculated center of mass. The next step is required so that the response spectrum analysis can utilize multiple mass locations. Moving masses around is considered nonlinear behavior, and thus we are going to define several nonlinear static load cases. We go to the load cases command and create a new load case named plus y mass with a type of nonlinear static. This allows us to set the mass source to mass plus y. The mass moved in the positive y direction. We do not need to define any other items on this form. We are using this case simply to set our mass location, so we do want to close the form. We repeat this step for a case named minus y mass. Which will use the mass moved in the negative y direction. Next, we go to the Define Modal Cases command. We start by reviewing our existing modal case. Note that it uses eigenmodes, and that the mass source is our original mass source based on the calculated center of mass. Also note that the maximum number of modes requested is 12, which is acceptable due to the fact that we are using a rigid diaphragm. We typically have 2 translational and 1 rotational degree of freedom per floor. We will leave this modal case as shown. We will copy the modal case and name it modal plus y. This case will ask for modes to be calculated based on the mass being moved in the positive y direction. To do this, we select the Use Nonlinear Case option and select our nonlinear case plus y mass. Remember that this case has no loads associated with it. The net effect of this is that it changes the mass source. Note that the mass source is now mass plus y, the mass we moved in the positive y direction. We will repeat this process, again copying the modal case, but this time naming it modal minus y, and selecting the minus y mass nonlinear case. This will result in the modal case determining modes based on masses shifted in the minus y direction. We are now ready to set up the response spectrum analyses using these new modal cases. Returning to the load cases command, we select our original seismic load case. However, this time the accidental torsion will be implemented by running response spectrum analyses with different mass locations, so we will set the diaphragm eccentricity option previously used to 0. Thus, no static torsional moment will be applied to this response spectrum case. Next, we will add 2 additional response spectrum cases for the shifted masses, copying the case seismic, which we will name seismic plus y. We will apply the same spectra in the U1 or X direction, but will now change the modal case to modal plus y. This load case will now use the modes with the mass shifted in the positive y direction. We repeat these steps to create a response spectrum case using the modes with the mass shifted in the negative y direction. We can now run the analysis. With the analysis complete, we start by displaying the deformed shape for the seismic case. This is the case where the mass has not been moved. Note that the displacement in the y direction is again virtually 0, as expected since there is no inherent torsion. However, when we display the shape for seismic plus y, There is now a significant response in the y direction due to the torsion that has been induced due to the shift in mass. Thus, accidental torsion can be accounted for dynamically by shifting mass locations without the need to worry about the amplification factors that might be required for torsional irregularity. This concludes this tutorial on the application of accidental torsion in ETABS.